So our first question here says, consider the differential equation dy over dx equals y minus 2 times x squared plus 1. Now, as soon as I see it say differential equation, I'm actually going to go look on my formula chart, and I'm going to paste that right here. Here we go. And let's follow these steps to figure this guy out. Our step 1 for part A says find y equals g of x, the particular solution. So right here I see that that's telling me particular solution. It's the same wording to the differential equation with the initial condition. I also see that this part right here is telling me of the initial condition. So let's get this done. Our first step says separate the y's and x's on the same side of the equal sign. So let's do this. Get some color coding here. Step 1 is y's and x's on the same side. I am going to divide by y minus 2 and multiply by dx. So I started off with dy over dx equals y minus 2 times x squared plus 1. Multiply by dx to get rid of this. Divide by y minus 2. So I'm left with dy minus y over 2 equals x squared plus 1 dx. My next step says to integrate both sides. Do this in green. So let's draw that integral here. When I integrate both sides, I should get that this is the natural log of the absolute value of y minus 2 equals, remember we're raising the degree and then dividing by that new lead coefficient, so it becomes 1/3 x cubed plus x plus c. This is very important here. My next step says we need to isolate y. So when isolating y, let's do this in pink. I'm going to exponentiate both of these sides, so that will cancel with that natural log, and I'm left with the absolute value of y minus 2 equals, I'm going to separate these two out, so I'm going to leave this e to the 1/3 x cubed plus x, and I'm going to be multiplying that by e to the c. Remember, my log rules state that if I'm adding things together, I can break that up into multiplying. My step 4 is to use that initial condition and find c. So I'm going to go back up and see what was that initial condition. It said that my initial condition was g of 0 equals 5 and y equals g of x. So I'm going to say y equals g of x, g of 0 equals 5. So therefore we have the absolute value of 5 minus 2 equals e raised to the, this all becomes 0, times e to the c. After that, I get 3. E of 0 is 1, so 3 equals e to the c. Same thing, to solve for that c, I'm now going to take the natural log of each side. So when I do that, guys should have been right there, I should get that natural log and that e cancel out, so I'm left with c equals the natural log of the absolute value of 3. Now I'm going to go back and plug this in because I know that natural log of the absolute value of 3 was supposed to go in for my value of c. And when I get that done, so this is working on part 5, we're going back to that step 3, working on step 5. So I have the absolute value of y minus 2 equals e to the 1/3 x cubed plus x times e natural log of 3. Remember that these cancel out, so I'm just left with 3. So this equals 3 e to the 1/3 x cubed plus x. And right here I have absolute value, and that means that plus or minus would work, but I want to get this boiled down to one or the other. I am given my initial condition that g of 0 equals 5. And because of that initial condition, so that I knew y of 0 equals 5, that because that is positive, then y has to be greater than 2. So that means that my absolute value of y minus 2 is just y minus 2. So I negate the negative version. So I'm just plugging this in right here. So then my final step is to make sure that y is isolated, so that means we're adding the 2. So my final step is saying y equals 3e to the 1/3 x cubed plus x plus 2. And we are good to go. Let's take a look at the AP scoring guide and see how we did on this question. All right. Now, this first part was worth 5 points. Feels like quite a lot. So let's get a breakdown of these 5 points. Now, right here it says that we got 1 point if we did separation of variables. Well, that was our very first step in blue. We did that. So that point would have come from that work that we did in blue. So this key is up here. So 1 point for separation of variables, we got that. It says we got 2 points for the antiderivatives. So that means 1 on each side. So let's look right here. That was our step 3. We did that in green. Or step 2, my apologies. So let's see right here, it says that we should have gotten the natural log of the absolute value of y minus 2. Good here. 1/3 x cubed plus x plus c. Good here. So we got those 2 points. Another point for the constant integration and uses initial condition. So that was kind of a shared point right there. So let's see what that meant. Constant of integration just means that we put that plus c. We did put that plus c. Uses the initial condition. That happens down here when we gave that initial condition g of 0 equals 5, and we use that to find our c value. So we used the constant, and then we actually found what it was. So all this work right here was another point. And let's see where those last few came from. So we're looking pretty good so far. Our last point came from solving for y, which we did. We isolated y. And let's see some notes that they made here. Max of 3 out of the 5 points if no constant of integration. So that means we did not put that plus c and we did not solve for it. Note 0 out of 5 if no separation of variables. So once again, if they look at your work and they see that you did not separate variables, so you did not move the y's over to one side, move the x's over to one side, they're not even going to look at the rest of your work. They're going to say, okay, we're done. All right, part B. Part B says, for the particular solution y equals g of x found in part A, find the limit as x approaches negative infinity of g of x. If I look at that part of solving limits on my formula sheet, it says always try to substitute first for limits as x approaches infinity. What we're really looking for, guys, is in behavior. That is the bottom line right here. So I'm going to rewrite this expression. So I want the limit as x approaches negative infinity of g of x. So I'm going to come here, part B. There we go. And the limit as x approaches negative or positive infinity here, we have a horizontal asymptote of positive 2. So that means that the limit as we approach positive or negative infinity is just going to be positive 2. Let's check out our score report to see how we did there. So not much information is given other than what we kind of already know. We know that we're supposed to say the limit as x approaches negative infinity and we get positive 2, and that's just 1 point for the answer. So we got that all going on right there. And just stamping this really quick, let me go over this. I noticed that this is going to be exponential growth. So make sure that you're thinking in your brain, you're like, okay, I know that the graph is going to look something like this. Remember back to all those pre-cal graphs. And so as x goes to negative infinity, that curve is going to be getting closer and closer to that horizontal asymptote of positive 2. For this final part, I just snipped a few of these pieces to pull them down here. It says consider that we're still considering the same differential equation. Let y equals f of x be the particular solution to the given differential equation with the initial condition f of 1 equals 3. Find the value of the second derivative at the point 1, 3. Remember our main variable, we're in terms of x still. Is the graph of y equals f of x concave up or concave down at the point 1, 3? Give reason for your answer. So we're asking for that second derivative because remember, second derivative does tell us something about concavity. Remember that if it's greater than 0, it's concave up. If it's less than 0, it's concave down. So we're trying to figure out what is the value of this and how does that relate to 0. So remember that D2, I'm just going to write some notes right here, is greater than 0, concave up. If it's less than 0, concave down. So just kind of wrapping our heads around what it's asking to do. Now I snipped and pasted this part on your formula sheet on implicit differentiation because that feels like what we're going to have to be doing here. I see right here that it's asking for my second derivative. I know that it's asking for my second derivative. So let's start to get that done. We know that dy over dx equals y minus 2 times x squared plus 1. Now I'm also given another condition here. I'm given that I have this initial condition of f of 1 equals 3. So I have this ordered pair. So what I'm actually going to do is I'm going to plug that in, and I'm going to say, let's actually find this first derivative given the condition or given the value 1, 3. And when I do that, I get 3 minus 2. Right here, I get 1 squared plus 1, which gives us a value of positive 2. Now the reason that I went ahead and did that is so that when I do get the value of that dy over dx, I know that whenever I see dy over dx, I can just substitute 2 given this initial condition. So let's move on and follow our steps. Let's get our original equation. We have dy over dx equals y minus 2 times x squared plus 1. I'm going to be taking the derivative of that. So I'm going to go over here and say that this is d squared y over dx squared. That equals we have product rule going on right here, so the derivative of y with respect to x, we have a constant, so that's 0 times x squared plus 1. Then we have plus, don't touch that first one, y minus 2 times the derivative of x squared is 2x. And earlier, I also saw that I gave this condition with that point. So I'm going to rewrite this. d2y over dx squared, given the condition 1, 3. Now this is important right here because you have to show me that you know that we're still using this initial condition. Our step 2 says plug in dy over dx, which is given. Remember, we actually have a value for dy over dx because we had an initial condition. So dy over dx is equivalent to 2 at the point 1, 3. And because we have that point as well, I can go ahead and plug this in. So every single time I see an x value, I'm plugging in a 1, and every single time I see a y value, I'm plugging in a 3. So that looks like 2 times 1 squared plus 1 plus 3 minus 2 times 2 times 1, which should give me the value of 6. Now we talked a little bit earlier about what we are looking for. So I know that this value is 6, and it asks if it is concave up or concave down. So the second derivative is 6, which is greater than 0. I know that's concave up, but remember I need to make sure that my answer is reflecting every single element here. So to summarize here, I'm going to say d2y over dx squared equals 2. Equals 6. d2y over dx squared is greater than 0 at my point 1, 3. And is continuous. Now I know that this is continuous because if I go back and look, there are no breaks, there are no denominators that could equal 0. So I can reach my conclusion and say because it's greater than 0 and because it is continuous, then y equals f of x is concave up. Let's look at what they scored. So the score guide here says that we get 2 points for evaluating the second derivative at the point 1, 3. Now this notation is important because you're saying given the initial condition 1, 3, and I did that. We did that right here. So we are good to go. And then I give the correct concavity with the reason. So we said concave up at the point 1, 3 because my second derivative is greater than 0. Great. I might add here at 1, 3 just because that was the initial condition. But we still said it was concave up, and we still gave a reason here. Let's just be super clear and make sure that we're naming that we know it's concave up at 1, 3 because that was our given condition.